Hey everyone, and welcome back to The Explainer. Whenever I look out at the natural world, this chaotic, swirling, incredibly complex physical space, I always wonder, how on earth do human beings actually manage to measure it, let alone predict it or solve its problems? Well, today we're going to figure out exactly how scientists and engineers kind of tame that chaos. We're looking at the process of modeling environmental systems. Think of it like an elegant, highly structured assembly line. We take the messy physical world and we turn it into solvable data.
So it really all boils down to one massive question, right? How do we make sense of the environment? When there's a nasty pollution spill in a rapidly moving river or a dense cloud of smog settling over a bustling city, scientists can't just guess what's going to happen next. They definitely don't just cross their fingers and hope for the best. They have to measure it, track it, and figure out how to fix it with absolute precision. But how do you take something as wild and unpredictable as nature and cram it into a format that a human brain can actually process and resolve?
Okay, let's dive right into this. Here is our four-part recipe for today. Number 1, the physical environment. 2, mathematical equations. 3, computer programming. 4, finding numerical solutions. And finally, number 5, we'll wrap it all up with modeling environmental systems.
All right, starting our assembly line with part 1, the physical environment, our raw materials.
Since the environment is, well, impossibly vast, we really have to categorize it into 3 manageable buckets. First up, water and wastewater. Now, we aren't just talking about a stagnant little pond here. Imagine tracking a chemical spill as it diffuses through a totally turbulent river system. You've got to factor in variables like flow rate, temperature fluctuations, and even sediment absorption. Second bucket, air and noise pollution. Think about how a dense cloud of smog settles over a city. That's influenced by thermal inversions, wind velocity, literally even the geometry of the skyscrapers. And noise pollution works kind of similarly, with sound waves actively bouncing off those urban canyons. And then we have our third bucket, solid waste and soil pollution. This gets into some really complex geological interactions, like how do heavy metals leach through different soil layers into our groundwater over, say, a span of decades. These aren't just abstract issues, They are dynamic, multivariable data sources. They form the incredibly complex raw inputs we absolutely need to kick off our entire analytical process.
Moving right along to part 2, mathematical equations, the blueprint.
So we've got our raw materials, and now we need a blueprint, which basically comes in 2 distinct mathematical flavors. Linear equations. These are fantastic for mapping out steady, straightforward relationships. Maybe you're calculating the static volume of a reservoir or a fixed rate of emission. Easy enough, right? But in the environmental world, things rarely stand still. That's where differential equations come in. They are literally the mathematical language of change over time. Say we want to track exactly how a specific pollutant, like nitrogen, decays while it's simultaneously being dragged down a fast-moving current. We use differential equations to capture that dual action. We're looking at competing variables, the physical rate of dispersion versus the biological rate of decay. By forcing the environment's behavior into these specific mathematical paths, we effectively translate a totally chaotic physical problem into a highly structured, logical format.
Which brings us to part 3, computer programming, the machinery.
Okay, to actually process all these complex equations, we need the machinery. We rely on 3 pretty heavy-hitting programming tools. Excel is great for organizing massive static data sets, like cataloging the daily tonnage of solid waste arriving at a city dump. But when you're tracking that nitrogen decay across a massive river system, you're going to need much heavier processing. That's where C++ comes in. It gives us the robust, object-oriented architecture we need to handle huge arrays of data really fast without the whole thing crashing. And then there's MATLAB. MATLAB delivers the high-level technical computing required to run thousands of differential equations all at exactly the same time. It is an absolute beast at complex matrix manipulations, letting engineers simulate, say, a pollution plume spreading across a 3D grid over several weeks. This software is the engine. It takes the mathematical theory of our environment and gives it the computational horsepower needed to actually generate real insights.
Let's speed things up a bit and look at part 4, finding numerical solutions, the final product.
When we finally run this computational machinery, we get a strict 2-step chronological outcome. Step 1, we get the numerical solution to all those gnarly differential equations.
The computer solves the math, generating these absolutely massive tables of data points that represent pollutant concentrations at highly specific times and locations. But let's be real, millions of raw numbers aren't exactly intuitive for rapid human decision-making, so we immediately jump to step 2, generating the solution and plotting the graphs. The abstract math is magically transformed into a visual, actionable curve, or maybe a predictive heat map. You can look at a dispersion graph and precisely pinpoint where air pollution is going to hit toxic levels next Tuesday at exactly 3 p.m. This step is a total game changer. It actively informs real-world policy, allowing civil engineers and city planners to authorize emergency evacuations or just instantly adjust chemical dosages at water treatment plants.
And this brilliantly illustrates our final concept, Part 5, Modeling Environmental Systems, the Big Picture.
So what exactly is modeling environmental systems? Basically, it's the sum total of the 4 points we just went over: environmental systems, plus mathematical equations, plus computer programming, plus numerical solutions. The absolute crucial thing to understand here is the deep, deep symbiosis of these pillars. It's like a giant puzzle. If you have a failure in data collection at the physical level, well, your mathematical equations inherit that initial flaw. Flawed math is going to break your computer code, and broken code renders that final numerical solution completely useless. You literally cannot model without accurate physical data, you can't translate it without the correct math, you can't scale it without the programming, and you definitely can't make informed safety decisions without those final graphical outputs. Together, they form this strict, perfectly interdependent toolkit for mapping our world.
Which leaves us with this final, kind of provocative thought. The next time you walk outside, I want you to look differently at the world around you. When you hear the roar of a noisy street, or you're just watching a flowing river, realize that it isn't just nature out there. It's dynamic data, just waiting to be processed. So are you ready to see the math and code hidden inside the environment? Because with this 4-step blueprint, you finally can. Thank you so much for joining me on this explainer today. Keep learning, keep looking closely at the world, and I'll catch you next time.